Okay, welcome back. Happy Wednesday. Today is class 29 for us. We are talking about related rates again. This is our second of 3 days talking about related rates problems. The reason we spend so much time talking about them is because they are so hard. We really need to hit them a few different days to try to get the basic concepts associated with those problems. Coming up, we've got quiz number 4 is going to be assigned on Monday. That is a take-home quiz. I'll give it to you Monday. You'll give it back to me Wednesday, right before the Thanksgiving break. Hopefully still making good progress on our 2 projects. They're going to be due right after Thanksgiving break. Questions on the calendar? And Thanksgiving break, it's on the it's on the sheet there. You can see that we don't meet on that Friday, which is we do meet Wednesday, the day before Thanksgiving, right? But there are no classes at GCC Thursday or Friday of next week for Thanksgiving. Other questions on the calendar? Okay, so looking here at page 22, I will tell you all right, so the daily summary says today we continue working on related rates problems, which we saw in class 27 2 classes ago. Here's the plan for today. We're going to do one related rates problem together, and then you guys are going to go back and continue the related rates homework, which was that scanned paper from 2 classes ago. If you finish that related rates homework early, or if you've already finished it before today, which is great, there are some more related rates problems on the next page in this packet, which you can work on during class today, okay? All right, so let's get started. First thing to do, take this number 0 and put a big old line through it. That should not be there. Cross that off. And let's take a look at the one problem we're going to do together. Number 1. It says ship A is sailing north and ship B is sailing east. Using an XY plane, radar records the coordinates of each ship. Approximate the rate at which the distance between the ships is changing at t equals 5. Okay, so this related rates problem is quite a bit different from the ones we were looking at last class, because here all we have are data points. So let's take a look at the data points for ship A. The first row has time in minutes, 1 1/4 minutes, 2 1/2 minutes, etc. And then we've got XY coordinates, which tell us the location of the plane at these different moments in time. So the first point that's plotted is X is 1.7 and Y is 2.71, and we can find that right here, right? 1.77, 2.71. And then I didn't plot this point, but the fact that it's still 1.77 means what's happening with the ship? It's going up, so we're headed north on that one. I did plot the last point, 1.77 and 3.67, that's here, okay? So this ship is heading north. Likewise, this ship over here, the first point is 5.24, 1.24, which is this guy right here. And then the last point, 6.08 and 1.24, which means this ship is headed east to the right, okay? And then it says approximate the rate at which the distance between the ships is changing at t equals 5. And so that's the distance between the ships is this black line that I've drawn in here. And so we're trying to find the rate at which that line is changing length, okay? It's definitely getting bigger as the ship goes north and the other ship goes east. I want to know the rate at which the distance is changing between these 2 ships. Okay, so I've got this picture, which is in my mind just sort of begging to be like I need to draw something else in here. And is it obvious to you guys what the extra stuff we need to draw to give us a shape that we've played with a bunch? We've got to get that right triangle. So let's draw the right triangle here. So I'll draw in different colors here. Purple can be this guy, and then green can be this guy here. Okay, so now we've got a shape that we can work with. And we got to think about, for example, purple. As the ship sails to the east, that purple is getting longer, yes? Which means I can't just put a number for how long purple is, because that would fix it. And I know purple is changing, which means purple needs a variable. So how about we just call X the changing distance for purple? Likewise, as the other ship heads north, green gets longer, and so green is changing. So can't put a number there, we need a variable. And then finally, the black thing, the hypotenuse there, also changing length, so it needs a variable as well. Okay, let's start filling in some things that we know before we write down an equation that we'll play with. So first of all, I want to know, what is this question after symbolically? It's the rate at which the distance between the ships is changing. The rate at which the distance between the ships is changing. What goes in that blank space? That's the z, right? It's the z is the distance between the ships. So dz dt is the rate at which the distance is changing. What is that equal to in this case? I want something even more elementary. At this moment, what am I putting next to this equal sign? Not a number, not a formula, a question mark. Okay? That's what we're after. Okay? We don't know what it is. We're going to do a lot of work to figure out what that is. Okay. Let's take a look at this t equals 5 business. So that's here and here. So when t equals 5, if we fix that moment in time, would you guys agree that x, the length of that purple, is a certain number? It isn't changing if we're just focused on that one moment in time. So I feel like we should be able to figure out what x is equal to. So let's put that here. X is equal to. When t equals 5, this ship is at the far right-hand point. Can you calculate? What do we need to do to calculate the length of purple, like the actual length of purple that I've drawn here? 6.08 minus 1.77. Yes, right? It's just the change in the x coordinates. So we'll put that up here. 6.08 minus 1.77. Somebody help me out here. 4.1 there, 3. All right. 4.31. All right. Likewise, I should be able to figure out what y is equal to at that one moment, t equals 5. So somebody else, what are we doing to calculate the length of y? 3.67 minus the 1.24. 3.67 minus 1.24, 2.43. So at the moment we're interested, when t is 5, we know what the x is as a number, we know what the y is as a number. We actually could calculate what the z is as a number if we need it. I'm not prepared to do that just yet, but if we need to find it, we will be able to find it. But now we need to get an equation. What's the equation that relates those three changing things? Which one? Pythagorean theorem, right? So let's use that. X squared plus y squared equals z squared. So again, for all these related rates questions, you got to pull a formula out of a hat. You need some formula that you got to come up with that relates the variables that you've named. And once we have that formula, what do we do to it? We take a derivative. Okay, so before we plug in, it's premature to plug anything in right now. No numbers just yet, but we take a derivative, both sides with respect to the variable t. What's the derivative of x squared? 2x times dx dt, right? Because x is not the independent variable, it's t here. So every variable depends on t, and every variable gets one of these little derivatives at the end. Plus derivative of y squared, 2y dy dt equals 2z dz dt. There we go. Well, yeah, we're gonna get information we're gonna plug in information right now, but we were taking the derivative of both sides with respect to t, and so even though the derivative of x squared has been 2x for us for like a month, that was when x was the independent variable, but now x depends on t, even though the relationship isn't like explicitly given here, and so that exactly. So so if we wanted to really be precise, it would be x is a function of t squared plus y is a function of t. Yeah, it's probably helpful to just like think about that every once in a while. because otherwise it, like why are we sticking on these dx dt's and dy dt's? Yeah, right. 2 times x of t times x prime of t. That's our chain rule. That's exactly what we've written. Yeah, good. Okay, so we're ready to plug. We're ready to plug in here, but the fact is we got all these 2's that we don't need, right? We can divide everything by 2 and just write a slightly simpler version of this. So I'm a fan of that. Okay, so now we start plugging in. X at the one moment that we freeze this problem in time. What is X? 4.31, we found that. 4.31 times, I'm going to put some parentheses there. dx dt, I don't know, we haven't done any calculations there. But let's keep filling in here. 4.31 times whatever dx dt is, plus the y is how much? Was the 2.43 in green, times dy dt. We haven't done any calculation there either, equals z. Do we know z? No, but we can find it. How do we find z? Pythagorean theorem, right? Okay, so what is it? 4.95 times dz dt. So Nick did the work for us. I'm just going to write pyth here. That's from the Pythagorean theorem. We all know how to do it. Okay, why am I okay putting a dz dt there, whereas I have empty parentheses for dx dt and dy dt? Yeah, dz dt is what we're after. That was the question, right? So like I'm quite happy putting that. But in the parentheses, I need numbers. I can't leave dx dt and dy dt. So we got to get numbers. If we can somehow figure out dx dt and dy dt, we put them in and we're done. Levi. That's what we're going to do. We're trying to find the rate at which, for example, the green ship is moving. We want the derivative of green as time passes, right? How much does green change by as time passes? That's just the speed of the ship. Now we have limited information about ship, I guess that's ship A here. We've just got 4 data points, but if I asked you how fast is this ship moving when t is 5, I think the only thing we could do is exactly what Levi says, is for this ship, we focus on t equals 5 and we look at a change in distance over a change in time, right? That's the definition of speed. That's our derivative. So let's do this in green. So right here, dy dt, I'm going to put approximately equal to, it's just a change in distance over a change in time. Change in y over change in t. So what am I calculating for the change in y? That's it. Just going to pick the 2 points, the point we're interested in is t equals 5, and then the closest point that we have is this t equals 3.75. That's all we're going to focus on is those 2 points. Downstairs, change in time. How did you get that? 5 minus 3.75. Everybody see it? Change in y over change in t. If you wanted to, you could find like a best fit line between the points, because there's no guarantee that this ship is moving at a constant rate. So there might not be a single line that hits all the points. What's that? They are in this case. Yeah. But yeah, so you could find like a regression best fit line. Typically, you say, well, I'm just going to pick the one point that's as close as possible to the point I'm interested in. And so that's ignoring the first 2 points and just using the last 2. Okay, what is this equal to? 0.256. Okay. And that's miles per minute. Okay, and then we play the same game with dxdt, which is over here in purple. So focusing only on these 2 points right here, dx/dt approximately equal to, so we're just looking for the change in x over change in t, change in distance over change in time. So what minus what on top? 6.08 minus 5.8 over 5 minus 375. Somebody with a calculator? 0.224. Again, that's miles per minute. And that's the best we can do. Those are our estimates for dx dt and dy dt. All we have to do is shove those things into our formula down here. So the first guy, and you got to make sure you put them in the right order. So the first guy is dx dt. That was the 2. What did we say? 2.24. Oh, 0.224. Did I write that wrong? No, I got it right. Okay. Can we get one more person to type this thing in? Up on top there in purple. Is it 0.224 or 0.124? All right. And then on the other side, the dy dt in green was 0.256. So we plug that in. 0.256. And now finally, finishing is easy. I just have to get a single number on the left-hand side and then divide it by 4.95. So again, somebody with a calculator, what is the left-hand side equal to? I could estimate it while you're typing it in, but then nothing. Okay, never mind. 1.1? 588 equals 4.95 dZdt. And then divide both sides by the 4.95. Three, two. I heard a 7 and a 1.
Well, I didn't round the 0.588.
So you said 7? Okay. 0, 7 or 7?
I got 0. I mean, I got
0.07. Okay. All right. So that's it. That's the rate at which the hypotenuse was changing length. It's about 0.32 miles per minute. And if you picked a different moment in time, we're not going to do the calculation again, but imagine that that we let this experiment go for a lot longer, and so the one ship is way up north and the one ship is way out east, and they're still traveling at the constant rates that they were traveling, right? What do you think about the rate at which this distance between my fingers is changing as they're close and as they get farther away? What do you think about the length between my fingers is increasing, right? I mean, like if we waited longer, that 0.32 would become a lot bigger number. The distance between these ships is increasing faster and faster. Okay, good. All right, so the reason I wanted to show this problem was just so that we have an example with data points. We had no formulas given to us about the ships, it was just data. Okay, all right, so on the next page, it tells you that the group activity is to continue working on the related rates homework, which was homework 27. It is going to be due on Friday coming up. I will remind you that this homework assignment is not right. This was the old one before I pared it down. So if you just go back to page 12, which is where the scanned problems are, you will see hopefully that you've written down the right homework assignment. So go back to page 12. And again, if you finish early the homework, or if you've already finished the homework, there are 3 problems that start right there on this page that you're going to work on now.